Just a video overview for the tech assignment C that is, Taylor polynomials. So the first thing you're going to do is go to Desmos, open a blank page, save it as something associated with tech assignment C. Just don't save it as untitled graph. What you're going to do is you're going to be assigned a function. You're going to create the Taylor polynomial for that function, and then use that in comparison with the Taylor series version of your original function. So I'm going to take you through an example here. Mine is going to be f of x is equal to e to the 2x. Now I need a equals f of c. Right? I'm just following this progression here. I'm going to let c equal some constant, call it 0. Normally it would automatically produce a slider whenever you put a constant value in. I think Desmos wasn't really sure what I was trying to do, so I type in some dummy value like 0 and then let it create the slider that way. Right? So when I hit enter, now I have a slider for f of c, and it gives a numerical value depending on where I am. Right? So then I'm going to figure out what the next term is going to be, because we can actually start building my polynomial here, because I have a c value. I have so I have f of c right here. Now I need f prime of c is times x minus c. So I'm going to do that as f prime of x. It'll graph it for us, which is nice. And then f prime of c, which I now have a numerical value for. All right, we'll do that again. I made a little note up here. You can use another function name for f prime and g prime and so on, because the primes can get a little out of hand. Right? So if you want to do it this way, what I would write is g is equal to f prime of x. So then later on I could say g prime, but you could really do it either way. It was more when I was doing this in GeoGebra, that was more necessary. Here, not so much. But for organizational purposes, maybe, I don't know. It's up to you. So, and actually, if we're building this, we don't really need the a equals either. So let me get rid of that. Right. So f double prime of my c, and that slider is going to get kind of lost in the mix, so I'm going to just bring that down a little bit. All right. And really, we don't even need the functions along the way, but I like seeing what the relationship is between the function and the actual original graph. So if I just did the f prime of c and f double prime of c, I wouldn't get the visual. I would just get the number. So it's kind of a preference thing. So then, I mean, you can go out as far as you want. Right, as far as Desmos will let you go. So I'll go f triple prime of c. All right, x first, sorry. F triple prime now of c. All right, so I get the function and I get the graph. And it's exponential, so the derivative is going to be pretty consistent. It's only off by a constant multiple. All right, so if at this point you feel like you've gone far enough, 3 derivatives is good. You can now build your model, and so you can build it pretty much the way you see it here. Like type all this stuff in. That's fine. Another way to do it would be what I was saying before, is you let this be equal to, for example, a, then b, then c, and so on. It's really up to you, right? But I'm going to write. It might not like this. I'm going to use f of x again, and maybe it'll work, maybe it won't. I might have to change that to g of x. I'm going to give it a shot though. So I'm going to take my f of c, right? So that value goes right in here, and plus f prime of c. So I'm really just kind of doing a lot of the same stuff over again, times x minus c plus f double prime of c. Right? So it's f double prime over 2 factorial. Right? So getting the factorials in there is going to be important. You could put the real value or you could put it as a factorial. So I'm going to do f double prime of c divided by 2 factorial times x minus c raised to the second power. And the thing about Desmos, I can keep typing in here and it's going to be perfectly fine, but I'm not going to be able to see everything. So that's one of the reasons. Oh, undo. One of the reasons why I had you do it kind of in an itemized fashion. You see, it doesn't really like that I'm using f again, so I'm going to go to g on that, and that corrects that issue. All right, I'm actually going to turn these off now. G of x, if I plot it, it doesn't show up. I'm just going to move it over here. It doesn't show up necessarily because we haven't most likely gone out far enough. Right, so that's going to be the next thing. And also, I mean, you look at these numbers; they're insanely large, right? So when I incorporate my slider, maybe I want to kind of dial back how far away from whatever c should be I go. I'll leave it at 0 for now. You see, it looks like a parabola. That's not quite what I'm looking for, but if I change it, it seems to kind of open up and then kind of move out of the way. So I'll go out a few more terms. So we'll do f triple prime, so plus f of c divided by 3 factorial times x minus c raised to the 3rd power. Okay, now it's cubic. Okay, keep going. F quadruple prime of c divided by 4 factorial times x minus 4 raised to the 4th power, back to a parabola. And at any point you can start kind of playing around with it. You can see it's sort of kind of getting a little wider there. You know, it's not quite a parabola. You can see that it's sort of taken on characteristics of the quartic equation. All right, so then plus divided by 5 factorial. Okay. And, you know, I turned off the original function, but if I bring it back, you can kind of see how it's sort of evolving into that shape. Let me change the color. Make that black a little thicker. 3. All right. Go out 6 terms. And really at this point, you could do a little copy-paste action. You know, so take this, copy, plus, paste, and just change your 5s to 6s. And throw on another little apostrophe there. See, it's slowly evolving, so keep going until it's a reasonable approximation of the shape of that exponential function. All right, so plus, oops, hit the wrong thing. So now we're going to 7 plus, now we're going to 8. Lost track of my apostrophes here, so I got to zoom in and count them up again. I got 1, 2, 3, 4, 5, 6, so I need 7, 8. And then just keep going from there. And you can see how it's slowly but surely getting to that. And you see this whole thing with the primes is really the issue, because if I have like the 30th derivative, that's a lot of primes to keep track of, all right? So you'll continue on with that until you get something that kind of lays the right way, all right? It doesn't have to be perfect, it just needs to be in the neighborhood. So I went out to the 13th derivative, and depending on where I place my c, it seems to line up better and better, and you get the idea now. So when we did f prime, f double prime, some of it was overlapping, but the more terms we go out, the closer it is to being an approximation. So it's sort of like wrapping itself onto the derivative. I'm sorry, the original function. Now what I'm also going to do is I'm going to upload, so insert image, appropriate form now, there you go. All right, so I have my work here. I'll grab a dot, drag it. All right, if you really want to make it like kind of stand out, you go in here and turn off the grid. All right, so that I have my work in there now. And I'm going to input this equation. Well, it's not in an equation form, but I'm going to call it, I could just do it as a summation, or I can name it. I can call it like h of x if I want, you know, whatever you want to. So I'll do h of x, I guess, equals sum. So just start typing the word sum and it comes up. 0 to some upper value. It's a calculator, so it doesn't really understand infinity, but you can put infinity in if you put, I think, yeah, you start typing it, or you could put a dummy value for n, which is what I'm for infinity, which is what I'm going to do. I'm going to put a capital N because I want to have a slider that I can manipulate, so I can actually show the wrapping part of this. Right, so 2 raised to the nth power multiplied by e to the 2a, e to the 2a divided by n factorial multiplied by x minus a raised to the nth power. All right, and so I'm going to go with all. Now it appears to just show a line, which would not be correct, but if I move this around, you see things are happening, all right? And if I move this around, you can see things are happening. So we want it to be the right kind of thing. So we use n as a placeholder for infinity. This only goes to 10, so let me go from 0, and I'll put in like, I don't know, let me put in 1,000, see if it handles that, and I'll go by tens, all right? And my a values, I'll leave that as a decimal, all right? So I'm going to, I'll bring it in a little bit, move it around. I'm going to make this a little thicker. Let me go with like a 5, just so it really stands out. You know, make it dotted too. Dotted or dashed. I think dashed looks a little nicer. So if I start moving this around, oh, it doesn't seem to like to. Hold on. Oh, because it didn't like my 1,000. So let me go 100. Oh, it doesn't even seem to like that. All right, so, oh, because I did step. My apologies. I put it in the wrong place. We want this to be 1,000 and that to be 10. All right, now it's going to work. And you can see it starts off as a line. Now it's slowly wrapping itself onto the original function. All right, so you can see. You know what? Let me turn off the red graph. I thought I turned off the red graph. Oh, yeah. There's a little bit of a lag because it doesn't like the large numbers, but that's what my exponential function looks like. So the Taylor series should be an equivalent value, or a function related to the original function, so equivalent to the original function. The Taylor polynomial, which we came up with here, because it doesn't go out to infinity, that should be more of an approximation, right? And the closer you are to the center of the series, whatever the a value is, the more accurate your model is going to be. It's kind of like the linearization stuff we learned back in Calc 1. All right, so when you're done with this, I know there's kind of a lot to it. Some of it, you know, you might feel is sort of unnecessary, like looking at this progression, but I like seeing what the numbers correspond to as we progress through the Taylor polynomial, because the whole point behind this one, I probably should have led with this, is to kind of see how, as you keep adding terms, your Taylor polynomial becomes, you could say, more accurate, but it gets closer and closer to the Taylor series, which is the equivalence to the original function. All right. So once you do that, save it, give it a nice title, and then share the graph into Brightspace. All right. And that's your tech assignment.